Yeah. So on to the good stuff, or the meat of the show, so to speak. You are a cosmologist. You've talked a lot about the Big Bang Theory, not the TV show, but the actual theory of how the universe came to exist in the state that it does. So if you had to describe the Big Bang Theory at the ninth grade level to the best of your ability, how would you describe it? There are doubters of science, and these stories that these scientists tell about where the universe came from, but how would you explain it to someone who doesn't understand?
So you have to realize in the universe, when anything happens, you can either say, okay, a thing is happening. What what is happening to try and either resist it or to try and keep it going? So I'm going to tell you that the universe, when we look out at it, we see all the different stars out there, all the different galaxies out there, as far as we can look with like the Hubble Space Telescope or any telescope. As far as we can look, there are stars and galaxies going back tens of billions of light years, right? Long time in the past. So when I say, what is the Big Bang? I first have to recognize an observation that came before the Big Bang, which is that this is a little bit puzzling. When you look at a galaxy, you're not going to see the exact same light that you see from the stars within our galaxy. We know that atoms are the same everywhere in the universe. A proton is the same, an electron is the same. The laws of physics, as far as we can tell, are the same. So if I have electrons orbiting on an atom, and the electrons cascade down the energy levels, they're going to emit light. They're going to emit light of a specific wavelength, right? A wavelength is what defines light. Well, here's an interesting thing. When we look out at galaxies, the closest galaxies to us, their atoms look like they're doing the same thing our atoms are doing. But when we look farther and farther and farther away, if I said, okay, hydrogen emits this line and this line and this line, it has these whole series of lines. When I look at a nearby galaxy, I see very similar lines to what I see on Earth. When I look farther away, I see these lines are actually shifted to
Is that
longer
red shifting?
wavelengths. It is red shifting. We say red because redder light is longer wavelength and bluer light is shorter wavelength. So we say red shift because these lights get shifted to longer wavelengths. The farther away a galaxy is, the more its light is red shifted. So why? Why is that happening? Well, the thing we realized over back in the 1920s and 30s is that this is because Einstein's equations actually predicts that the universe is going to expand. If I take a universe and I fill it with matter evenly and I say, don't expand, what's going to happen? The whole universe will collapse fast. It will just collapse into a black hole, boom, singularity, game over. That didn't happen. And that isn't happening now. So instead, you say, okay, well, look, what is happening if I take this universe and I fill it with matter and I say, hey, physics, right? Astrophysics, cosmology, come on, do your math. What's going to happen? I actually get two solutions. Just like if I said, hey, Bryce, what's the square root of 4? You would tell me 2, and I would go, are you sure? And you'd go, oh, crap, he's trying to trick me. And you're correct, because it could be 2 or it could be -2. Right? 2 squared is 4, but -2 squared is also 4. When we put those equations in and we solve them, we find that, the universe could be expanding or it could be contracting. The equations don't tell us. You have to actually look at the universe and see what's it doing in order to know. And so we see this and say, oh, it is expanding. So this expanding universe is where the idea of the Big Bang came from, to say, okay, look, we see all these objects out there, galaxies, and the farther away they are, the more the light is redshifted. So that means the universe is expanding today. Well, if it's expanding today, that means in the future, it'll be bigger and less dense. And that also means earlier, it was smaller and more dense. So the universe began from a hot, dense state and expanded and cooled to become the way it is today. The Big Bang is the earliest moments that we can describe the universe as hot, dense, full of matter, and expanding. So I would say, if you ask me what's a simple version, now that we've had all this, 5 minutes of background, how would you describe the Big Bang? I would say the universe is a race. It's a race between the expansion of the universe, whatever this initial expansion was, which works to push everything apart, and gravity, which works to pull everything back in. It's this attractive force that works to pull everything back together and slow the expansion rate down. So the universe is a race between expansion and gravitation, and the Big Bang is the starting gun of that race.
And if I were to ask you to elaborate a little bit at the slightly higher than ninth grade level, I'm sure a lot of people would be curious about why that's happening. And my basic understanding is it has to do with the things in the universe that we don't exactly see, but we know has some sort of an effect. So we hear about these terms like dark matter and dark energy and inflation, and they all seem to be related to this idea of the expanding universe. So what are they?
Sure. Let's just take on the big three all at once. So, okay, if I said, okay, look, so you're a smart guy. You said, okay, we're going to start off with this hot, dense, expanding thing, and we're going to let it expand and cool and get less dense, and then it'll gravitate and form stars and galaxies and blah, blah, blah. And here we are 13.8 billion years later. Fun story, right? Well, here's the thing. If I start off in the early universe and I say, hey, guess what? If my universe is full of stuff and it's really hot, won't all these atomic particles, subatomic particles, won't they all try to fuse together when things are very hot and dense like they do in the center of the sun and all stars? Won't they try to make heavy elements and fuse together and have these runaway reactions? And the answer is the universe would love to do that. But it has to wait. It takes time. So let's say we're trying to grow the stuff in the universe. If I said, I've got this sea of particles out there and I want things to fuse together, what needs to happen? It turns out you can't be too hot, because the way you build up heavy elements is through a chain reaction of nuclear reactions. So you say, oh, well, I'll take a proton and a neutron and I'll fuse them together and make deuterium. And then I'll take deuterium and another proton and fuse them together and I'll make helium-3. And then I'll take another deuterium in there and I'll get helium-4. And then I'll take 3 helium-4s and smash them together and get carbon. I've got this big chain reaction that's happening, right? Only the early universe works against you because things are hot. So you try to take that first step and say, oh, proton, neutron, deuterium, and now I want to form something else, but oh crap. 10 to the minus 17 seconds pass, and a photon comes in and it hits my nucleus. And what happens? A photon has so much energy that it splits them back apart. And you say, crap, well, I have to play this waiting game then. I have to wait until these photons from the early universe, these high energy, short wavelength photons, they have to redshift. They have to get cooler so that eventually I can form deuterium and not destroy it right away. So you say, okay, well, I'm going to do some math and I'm going to say how much of all the different elements should I get depending on what's in my universe. So you work out the math and it turns out that, in the early stages of the universe, you can get about 75% hydrogen, 25% helium, about 0.1% leftover deuterium or helium-3, 0.01% maybe, and then 1 part in 10 to the 9, 1 part in a billion is lithium, and nothing else. And you look at that result, you look at what you get and say, geez, well, I measured the expansion rate of the universe, and I knew all the combined stuff in it has to account for it. But when I look at how much matter do I have from these observations I made and the laws of nuclear physics and the framework of the Big Bang,
There's not enough.
Not only is there not enough, there's not enough by like a factor of 20. There's like got to be 20 times as much stuff as all the normal matter combined. So I say, okay, well, I have different ways of measuring the universe. So I can look at the cosmic web, and I can look at how galaxies cluster, and I can look at the leftover glow from the Big Bang, and I can look at these light elements from the Big Bang, and I can look at distant supernovae and other what we call standard candles, objects that we know how they work, so that when we see them far away, you can just say, oh, it's like a 50-watt light bulb. I see that thing and it looks faint, but if I know it's a 50-watt light bulb, then when I measure how bright it is, I can know how far away it is. So that's another thing that we do. So we bring all this together, and that's where we say, you know, about 2/3 of the universe is some type of energy inherent to the fabric of space. That's what we call dark energy. And about 1/3 of the universe total is some form of matter.
Mm-hmm.
But if only 5% is normal matter, then the other 27, 28%, it has to be some other kind of matter that doesn't absorb light, emit light, or interact with the normal matter by smacking into it. So that's what dark matter is. So we don't know exactly what they are because it's not like we can directly detect them, but we can indirectly detect them. We can look at them and see their effects. Mm-hmm. And since we know how gravity works, and we know how cosmology works, and we know how the expanding universe works, we can be confident in a whole slew of different ways that dark matter and dark energy are real, but we don't know what they are. Inflation is a little different because inflation is basically saying, look, if you went and said, hey, you know, Big Bang genius, I'm going to take this universe that we have now and go back in the past, smaller, hotter, denser, smaller, hotter, denser, smaller, hotter, denser. Why stop? I'll just go all the way until everything's in a tiny little point, until everything's in a singularity, right? Where all of space and all of time and all the matter and all the energy is compressed down into a single point. That was originally what people thought to do, but it turns out if you make that extrapolation, the laws of physics actually predict you will see a whole bunch of things that we don't actually see in our universe. So this was a problem that people working on the Big Bang were aware of and were thinking of in the 1970s. And in the early 1980s, that's where the theory of inflation came about, because people were asking the question, look, you can either tell me, okay, look, somehow the universe at the hot Big Bang, at the start of the hot Big Bang, it was born this way and it had these properties and no one knows why. And that's the end of the story. And if you say that and you're a scientist, I'll say, okay, at least try.
That's giving up, isn't it?
Try. To me, it is. To me, it is, because in science, if you say, okay, look, we see things started off this way with these initial conditions, what we love to do is we love to look for a mechanism. We ask ourselves, what could have given rise to a system that starts off with this initial set of conditions, right? So this is basically saying, I want to supersede the Big Bang theory, right? Again, not the TV show, the theory. So if I want to supersede it, what do I have to do? I always say there are 3 things you have to do if you want to replace an old scientific theory. Thing 1 is everything that the old theory succeeds at, you have to reproduce those successes. If you're like, hey, I've got a theory and it does all this great stuff, and I'm like, well, I've got an alternative that doesn't do that great stuff, you tell me go home until you do, because that's correct, right? I can't come to the table with something unless I could say, hey, everything your theory does, my theory also does. So it has to first off not obviously be wrong, because if I can't do the things that the existing theory already does, I'm obviously wrong. The second thing you have to do is say, look, I tried to explain something that the old theory didn't explain. Can I do it? The answer better be yes, right? This is how Einstein got his start with general relativity. He said, Newton, you're great, you succeed at all these things, but you can't explain why the orbit of Mercury works the way it does. So for Einstein to get started, he had to come up with a theory that worked the same as Newton's theory, where Newton's theory succeeded, and in that one place where it failed, his theory had to succeed. So that's a second thing it has to do. You're saying, okay, look, for inflation to replace the Big Bang, it has to give you this hot, dense, uniform, expanding state, and it has to explain why the universe was born with the set of properties we see and not with the set of properties we'd predict without inflation. And then you have to do a third thing that is even more difficult. You have to make novel predictions that differ from the original theory's predictions that people can go out and measure and see, is the new theory right or is the old theory right? And so if you can do those three things, then you can advance science and you can have a theory that replaces the old one. And that's what inflation says, is that, you know, if you had a phase of the universe where it wasn't filled with matter or radiation, but instead just energy inherent to space itself, that's going to make space double in size and double in size and double again in size. And very quickly, in a tiny fraction of a second, you will go from a subatomic scale to something that's inflated to be larger than the size of the visible universe. And then when inflation comes to an end, all that field energy gets dumped into matter and radiation. And that's where the hot Big Bang gets started. But the big things that make it different from the hot Big Bang without inflation is you don't get up to an arbitrarily high temperature. There's a cutoff. You only get as hot as that field energy from inflation allows you to get. And it also predicts, because of quantum physics, that when you have this inflating space that expands very rapidly, these little tiny minuscule quantum fluctuations, they get stretched to all different scales across the universe. So we predict with inflation that the universe should have been born with little tiny imperfections somewhere like on the 1 part in 30,000 level, where some places are more dense than others and some places are less dense than others. And we can actually predict, based on the spectrum of fluctuations that inflation should give you, what type of cosmic web should we get out. And that, again, when you take all that information and you gather all the data and you compare it to what you predict, that's, again, how we know, oh, well, it makes sense if you have dark matter and dark energy and inflation, and if you take any of those ingredients out, the observations don't match up anymore.
Wow, that was a lot. And basically what I took from that is we can be confident that inflation is not superseding or it's not abolishing, so to speak, the Big Bang Theory. It's adding to it. Is that?
I would say that's fair. Basically, if you say, okay, according to the Big Bang, the universe came from this hot, dense state, that's still correct. But if you want to say, oh, the Big Bang implies we go all the way back to a singularity, and then the universe Hadoukens itself into existence, no, not to a singularity. That's too far, right? You made an assumption early on, right? Back in 1927, right? Lemaitre made this extrapolation and he called it the primeval atom, or the cosmic egg, that goes all the way back to like one thing where everything starts from. And that's not a good assumption. We thought it was for about 40 years. And then we started realizing, if things got arbitrarily hot and dense, and it didn't ever expand at these inflationary speeds, then you would expect to see a different temperature in that direction versus that direction. When I look to the limit of what I can see here and there, why are they equal to 99.997% in any two directions I pick if they've never had time to communicate to each other? But inflation will fix that for you by saying, oh, well, when things expanded like that, then the thing over here and the thing over here, they used to be connected in the past. So when you're saying, why are they the same? It's because they used to be the same. And the inflating space just drove them apart. So there are, I'll just say there are at least 4 separate independent tests of inflationary Big Bang versus no inflation in the Big Bang that have been conducted, that we've gotten results back. And inflation is 4 for 4, and the Big Bang without inflation is 0 for 4. So there are still people out there who are like, well, but we could do this other test, and I'm waiting on the results of this test before I say that I believe this. And
It
I'm
sounds like
look,
we've settled it. It's
like
inflation until
you might need to convince yourself, but I'm thoroughly convinced because either inflation happened or something that is hitherto indistinguishable from inflation, but somehow isn't inflation, happened. So at this point, I'm content to say, look, I can't tell you the particulars of every aspect of inflation that happened. But if you're saying like, well, what if inflation didn't happen? And I'm like, okay, well, now you're in like Wayne's World territory and are asking me about monkeys flying out of my butt. Like it might be this monkey theory alternative that you have, but I don't have supporting evidence for that. Whereas inflation has gone and met all 3 of these very high bar to hurdle criteria that we've set up.